So in section 3.3, we're looking at simultaneous equations and graphs. And you may well be familiar with this already, but it is worth making sure you've got straight in your head all the ideas here. So I'm going to take the example in the book, as usual. And I've got 2x plus 3y equals 8, and that is this line here. Now let's just pause for a minute. What does that mean? 2x plus 3y equals 8 is a thing in algebra. This line is a geometrical thing, right? It's a straight line. So what does it mean to say that equation is this line? Well, it means two things. It means that if you get a pair of numbers x and y that solve this equation and you turn them into coordinates, they are on the line, okay? So any pair of numbers that solve this equation is on the line. Now that could mean, so far that could mean this. That could mean, okay, there are 5 sets of coordinates that solve the line, that solve the equation, and there are those 5 crosses there. That all the solutions to the equation are on the line. That's half of what we mean when we say the line and the equation are the same thing. The other half of what we mean is, if there is a point on the line, it solves the equation, okay? So every point on the line solves the equation, and every point that solves the equation is a set of coordinates on the line. If we just had the fact that every point on the line solves the equation, it might be the case that all of these coordinates on the line solve the equation, and there are some more that solve the equation as well. But that's not what we mean. We mean that the points on the line are the solutions to the equation are the points on the line, and there are no points that solve the equation which are not on the line, and there are no points that are not on the line that solve the equation, right? We mean that those two things are exactly the same. So there are infinitely many solutions, x and y pairs, that make this equation balance, and all of them line up neatly if we draw them on a set of coordinate axes. And that's true for any equation any sort of equation in line, right? So 3x minus y is 23, and that's this line here. So if I'm looking for a solution to this equation and this equation, I'm looking for a simultaneous solution. If I take those two as a pair of simultaneous equations, what I'm saying is I want an xy pair that solves this equation and an xy pair that solves this equation at the same time. Well, the solutions to this equation are all on this line. The solutions to this equation are all on this line. So where is the solution to both of them? It's got to be there. It's got to be a point that is on both lines, because there can't be any other solutions. There are no solutions which aren't on the lines. So if we understand what we mean by this equation is this line, then the rest of it is just a logical consequence, right? So that point there is the only point which solves this equation and this equation. It must be, because straight lines are straight lines. They're only going to cross at one point. They can't turn round. They can't sort of curve and cross over here somewhere or down here somewhere. We know they only cross at one point, so that is the only solution to this pair of simultaneous equations. Okay? Now, in the same sort of way, if I've got a quadratic and a straight line, it doesn't have to be straight lines. What does it mean for this quadratic to represent a particular quadratic equation? It means that the solutions to the equation are the solutions on the line, and so on, right? So if I take this quadratic and a straight line, the crossing points are the solutions to the simultaneous equations. Now, I should point out that often this sort of thing happens. We end up with y equals 2x plus 3 and y equals, I don't know, 4x squared plus 6x plus 4. And people say, okay, I've got those two equations. Where are the crossing points? And I have students saying, oh, you put the equations equal to each other. And that's the point where I get really grumpy and I say, no, you don't put the equations equal to each other. What you do is you take those two equations and you solve them simultaneously by substitution. So you substitute from equation 1 into equation 2. Every time you see a y in equation 2, you replace it with this. So you sub from equation 1 into equation 2. And what you get is 2x plus 3 equals 4x squared plus 6x plus 4. Okay, so every time you see this y, you replace it with 2x plus 3. And students then say, yeah, that's what I meant. You just put that equal to that. But can you see, we cannot put an equation equal to an equation. An equation has to have an equal sign in it. So I can't put this equal to this. What I can do is I can put this equal to this. Fair enough, you can do that. But it's much better for you to think about it as substituting from equation 1 into equation 2. And here's the reason why. First of all, what if I don't give you an equation which has got a y on one side? I've seen so many students say, well, I'm used to just putting the equations equal to each other. So they take whatever's on the right-hand side and put it to equal to whatever's on the right-hand side over here. That only works if you've got only y's on the left-hand side, right? So I'm looking at the mistake that people would make, and maybe you think this is a silly mistake, but I've seen it done lots of times. You've got an equation here, an equation here. We draw them on the graph. We want to see the crossing points, and people think crossing points put equations equal, so they would write down 2x plus y equals x squared minus 3x plus 1. And of course, you can't do anything with that. So it's not put the equations equal, it is solve the equations simultaneously. If you're lucky and you have the functions given to you in a nice form, the substitution stage is really simple. It's just 2x plus 3 equals 4x squared plus 6x plus 4. But you think of that as solving simultaneous equations, okay? The other reason you need to think of it as solving simultaneous equations is because you get this idea in your head. And again, if you're in my class, you are trained into thinking of this, I hope. Where do two functions cross? Solve the equation simultaneously. That's always the answer, okay? And it doesn't matter if one is a circle, one is a reciprocal, one is a quadratic, one's a cubic, whatever you've got, two equations cross, you want to solve the equation simultaneously. And that's going to help because things like statistics and mechanics and the pure course later on, when we've got all sorts of things in context, if in your head you see two graphs, two functions drawn as graphs, and you're looking at some crossing points, you want to automatically be trying to solve the two equations simultaneously. That is almost always going to be the right thing to do, okay? Now, last thing to say on this section, if you have, and in this section we're specifically looking at quadratics. If I have a quadratic and a straight line, I could have any of these situations, which should be ringing a bell perhaps from when we looked at roots of quadratic functions. A straight line could go through the quadratic at two places. It could just touch it and be a tangent to the quadratic, or they could miss each other altogether and there could be a gap between the two. And you can perhaps see, when I solve two simultaneous equations, one quadratic and one not quadratic, halfway through I end up with a quadratic equation, okay? So algebraically, what do these situations look like? Well, if that quadratic there has two solutions, I'm looking at this. If that quadratic there has one solution, I'm looking at this. If that quadratic there has no solutions, I'm looking at this. So we need to kind of get the link between those things. 1, 2 or no solutions. Halfway through the algebra we get a quadratic that has 1, 2 or no solutions. So what 1, 2 or no crossing points means 1, 2 or no solutions. And the typical question they might ask would be, they would give a, let me just see if I can see one. I can't see one easily. But the typical sort of thing would be they'd say, okay, here's a quadratic, sketch it, and you sketch the quadratic. And then they say, here is a straight line graph, sketch the straight line graph, and you draw that. So this is what your diagram will be looking like, X, Y. And they say, from your diagram, give a reason why this quadratic equation has no solutions. And this quadratic equation would be the one that you get when you take the equation for this line and the equation for this graph, and you try and solve the two simultaneously. This quadratic equation pops out. So if you understand the links between all of these things, then that question is kind of obvious. You're saying, oh, you're asking me for, I've got a quadratic and a straight line. They're not crossing, so there are no solutions when I try and solve the graph simultaneously. And then part B, when it says, oh, so why are there no solutions to this quadratic? If you hadn't got all those links in your head, that would be a really weird question. We started with graphs and drawing graphs, and now why are you asking me about a quadratic with no solutions? What's going on? Well, the reason is you can see the links, right? You're thinking, okay, well, quadratics with no solutions, I'm thinking of diagrams like this, where the x-axis hits the quadratic at different places. I've just drawn a diagram like this, which has got a straight line graph not hitting a quadratic, so I take those two things and solve them simultaneously, and, okay? So that is everything on that section 3.3, which is, yeah, that's the last bit. The chapter 3 is equations and inequalities, so we've dealt with the equations part of the chapter, and we will carry on with the inequalities part of the chapter in the next video.